Welcome to Online Algebra 2. This is section 5-6, the Fundamental Theorem of Algebra. Our objective for this section is to use the Fundamental Theorem of Algebra and everything we've done in the past sections of Chapter 5 to solve polynomial equations for all their solutions, which include complex solutions. And what you need to know is that you can factor any polynomial of degree n into n linear factors. But sometimes the factors will involve imaginary numbers. And that's pretty much what the fundamental theorem of algebra is all about. It says the degree of the polynomial of the equation tells you how many roots the equation has. And it's easy to see this graphically for a polynomial of degree 1. It's just a line, right? It has a single zero, right, wherever it crosses the x-axis. But when you look at, unless it's a horizontal line, of course, then it's a little bit different. But if you look at these three parabolas, okay, these are all degree 2. You can see that there's a couple different choices that happen. Here, on the first one, this graph crosses the x-axis twice. So it has two real zeros. This one hits the x-axis and bounces the other way. So we should remember that it has one real zero, but that real zero has a multiplicity of 2. So it still has two answers. This one has no real zeros. It doesn't cross the x-axis. But yet, that exponent there tells me that I should have two answers, which means that the two answers are going to be imaginary. They're going to be have something to do with I. Okay. Cut off a little bit there. All right. So when you factor the rest of them, you can see that it has two real roots. This has a root with a multiplicity of 2, and this one is my two imaginary zeros. So every quadratic polynomial has 2 roots, every cubic polynomial 3 roots, and so on and so on and so on. And this is related to the fundamental theorem of algebra. And the German mathematician Carl Friedrich Gauss is credited with proving this theorem. Okay? And it basically says that if you have a polynomial and its degree is 1 or more, then that polynomial has that many roots. If you count every multiple root as an individual root, and then any complex roots as a complex as well. And remember that complex roots come in pairs. So if you have 1, you're going to have 2 conjugates. Okay. Short version here is whatever the degree, that's how many answers you need to get. Let's try it. So here is a 5th degree polynomial. Okay. I am going to get 5 answers. I could try to factor this with something, but there's no technique that I know that I could factor right off the bat with something like grouping or quadratics or something like that. But I can take the factors of 4, plus or minus 1, plus or minus 2, plus or minus 4, and guess, divided by the factors of 1, which is just 1, and guess one of these 6 numbers that might work here, test it with synthetic division, and then see if it is a root, and then move on from there. So let's try it. Let's start with 1. So that's 1, negative 1, negative 3, positive 3, negative 4, positive 4. Check for any missing roots. 5, 4, 3, 2, 1. No? Okay, good. So bring down the 1, multiply, add, there. That's a negative 3. Adds to 0, multiply, and if we look at that, we get a 0 as a remainder, which means that 1 was a factor, which means that x minus 1, or sorry, 1 is a root, and x minus 1 is a factor of this polynomial. Now, this is a weird pattern right here. Remember that dividing using synthetic division reduces the degree by 1, so that leaves me with x to the 4th minus 3x squared minus 4. And now, because of this pattern that I have here, that I have fourth power, second power, and then down to 0, now I can factor this using quadratic techniques. But instead of putting an x in the front, I put an x squared. Factors of 4 that subtracted 3, x squared minus 4, x squared plus 1. This factors a little bit more, x plus 2, x plus 2, x minus 2, because it is the difference of two perfect squares. And the sum of two perfect squares doesn't factor into real terms, but it does factor into imaginary terms. So that's 1, 2, 3, 4 answers. I should have 5, but don't forget about this one. So we have x minus 1 as well. Okay, so I have successfully factored this polynomial into 5 linear factors, which gives me my 5 roots as 1, this one, plus or minus 2, these two, and plus or minus I, those two. 5 answers. Okay, let's try again. So again, the first step here is to set the polynomial equal to 0 minus 13x squared plus 10x, setting it equal to 0. I see a common factor, so I'm going to factor out the common factor. And then I can just focus on this piece in here. Unfortunately, it doesn't look like grouping is going to help me, so I'm going to guess a possible rational root that will. And it's going to be, let's check 1, 2, negative 13, 10. I'll come back to the x later. Let's just try to factor this bit right there using this technique. 3, negative 10, and look at that. One was a factor of this polynomial, a root of this polynomial. And remember, the leftover is now 1 degree less. That was a 3, so now this is a 2. X squared plus 3x minus 10, which factors into x minus 5, x minus 2. Okay, so that means this polynomial in factored form is x times x minus 1 from this root right here, and then these two, x minus 5, x minus 2. By setting that equal to 0, we can say that x is equal to, remember, if the variable is by itself, that's a 0, 1, 5, and 2. 4 answers, just like the degree of this polynomial. Okay, so if we had a graph to help us, we could factor this a little bit easier. So right now I know that there's going to be 4 zeros. We'll just look at this graph. There's only 2 places it crosses the x-axis. So that means that, now I didn't need the graph, right? If you didn't have this, you could guess the factors of 18 that could work in this equation, but maybe a graphing calculator might help you, okay? And in fact, it shows me that negative 3 and 3 are roots of this polynomial. So let's divide them out using synthetic division. 1, 1, minus 7, minus 9, minus 18. 4, 3, 2, 1, 0. Good. And let's try it. Bring down the 1, multiply, add, multiply, add, positive 5, positive 15, positive 6, and a positive 18. And it really needed to work. If this didn't work, I would have done something wrong because I can clearly see that it is a root. in the graph. Now, the goal is to get this down to x squared. This is 1 less. This is x to the third. But I also have another 0. I also know that negative 3 is a 0. So don't just go back to the beginning and try this again. That doesn't really help you. Divide the negative 3 out of the resulting polynomial. Okay? And watch what happens. We bring down this 1. Now we multiply it by negative 3. I get 1, negative 3, 2, negative 6, and 0. Now, my new resulting polynomial is x squared plus x plus 2. Okay? And I can set this equal to 0 to try to factor it. Unfortunately, even just looking at the graph, I see that it's not going to factor because the graph does not cross the x-axis anywhere. So that means my only choice to get the 2 remaining roots is to use a quadratic formula over 2a. So we have negative b plus or minus b squared minus 4 times 1 times 2 all over 2. So that's negative 1 plus or minus the square root of 1 minus 8, which is negative 7 over 2, which leaves me with my next two answers, negative 1 plus or minus I radical 7 over 2. Okay, so this is 2 roots, plus and minus. These are my other 2 roots, and now I have 4. I have all 4. Okay, so if you have access to a graphing calculator, if you see something that would work well, then you can use the graph to help you solve the rest of the function. Okay. Here are the equivalent ways to state the fundamental theorem of algebra. Okay, every polynomial has of degree n has exactly n roots, including multiple roots. It has n linear factors, and it has at least one complex zero. Remember, complex numbers are real numbers and imaginary numbers. So if the degree is 1 or bigger, it is going to cross the x-axis or have an imaginary answer somewhere. It's going to have at least 1. All right. So what can we do with all this stuff that we've learned in this chapter? Let's put it all together. And you should be able to answer all of these questions about this polynomial based on everything that we've done so far in this chapter. Okay, let's go through it with this one and see what all the answers are. Okay, so first of all, classify the polynomial in degree by number by degree and number of terms. This was in section 1. So this is a cubic polynomial of 4 terms. Describe the end behavior that I get by looking at the first term, right? Because it is positive and odd, the left side goes down, the right up. The maximum number of turning points. Well, this graph, any graph, can turn 1 less time than the degree. So the maximum number of turning points is 2. Okay. These next couple, and let's bring this down so we can continue. Ooh, whoops. Let's bring this to the front. There we go. Let's bring this down so we can continue to talk about it and see it. All right, so the number of complex zeros. So basically what this is asking us is how many answers could this have? And like we just talked about from the fundamental theorem of algebra, this could have 3 answers because it's to the 3rd power. Now, here's where we have to use a little logic. How many of those answers could be real? Well, All of them could be real, right? Because you can have a third degree polynomial that crosses the x-axis 3 times. Okay? Could 2 of them be real? Well, let's think about that for a second. If 2 of the answers were real, then what's the other one? Because there's going to be 3 answers. If 2 are real, that means the other one's imaginary. And we should remember that imaginary numbers have to come in pairs. They have to come in conjugate pairs. So you can't have 1 real answer, or sorry, 2 real answers and 1 imaginary answer. So this is not possible. But we could have 1 real answer. Now, this is not saying how many answers this thing has, how many of these answers are real. This is just saying, how many are possible? So it could have 3 real numbers. It could have 1 real numbers. It could have 0 imaginary or 2. Because imaginary zeros always must come in pairs. And these 2 questions kind of go hand in hand with each other. All right, the possible number of positive and negative real zeros. In order to solve this, we use Descartes' rule of signs. So now we're looking for the number of sign changes in this expression. There are no sign changes in the original expression. But to get the next one, we have to put a negative in for x, which changes the sign of every term with an odd exponent. And now the sign changes once, twice, 3 times. So there are 3 or 1 negative real zero. Remember positive real zeros? We look at the original expression, whatever number we get, we keep going down by 2's until we get to 0. And same thing with negative real zeros. We look for the number of sign changes and we go down by 2's. The possible rational zeros. Possible rational zeros are the factors of the first term divided by the factors of the last term. So that's plus or minus 1, plus or minus 1/3. Okay. And finally, the last thing we're going to look at here is the factors and the actual zeros, and then we'll graph it. So now we have to actually factor it. And I'm going to take these, I'm going to take these 4 possible zeros, and I'm going to see if any of them work. 3, 7, 5, 1, using synthetic division. Bring this down. 10, 10, that's a 15. That's not going to work. Let's try -1, and I'm going to hope this works because otherwise this will get a little more complicated. -3. So that's 4, -4, 1, -1, and 0. Good. So here's my first factor, x plus 1, and my actual 0 is -1. Okay, now remember that this is 1 degree less. Okay, set it equal to 0, and I should be able to factor this. So that's a 3x and an x. Everything is positive. Double check using FOIL that it works out, and it does. So those are my other 2 factors. 3x plus 1 and x plus 1. And my zeros become -1. Ooh, well, I could write it like this. And a better way to write it is like that. So it becomes -1 with a multiplicity of 2 because it happened twice, and -1/3. And we see that both of those, or all of them, are in my list of rational zeros. Okay, so we can take all this information and help me graph the polynomial. I know at -1, this graph is going to touch the x-axis and go the other direction. Let me pull down the formula again. Okay. I also know from way up here that the left side goes down, the right side goes up. So I also know that this side goes down, this side goes up when I'm done, okay? And now the next thing to do is make a table with the rest of your answers. I also know that this graph intercepts at a third. No, negative a third. What was it? Yeah, negative 1/3. So that's like right there. That's not super helpful. We'll get to the rest of that. Let's plug in a 0 to get the y-intercept is 1. Okay, right, just plugging in 0. Now you don't really have a lot of choice. Okay, so we basically know that this side has to go down somewhere. So we know our graph is going to be coming from this way. I know it's going to touch here and then sort of has to go back to here. So it's not going to go straight. Graphs don't do that. It's going to touch here and it's going to have this little loop and probably go straight up because it can't turn again. This graph can only turn twice. So that means if it turns here as once, it's got to go back up there. So it cannot turn again. So odds are this number, if I plug in 1, is going to be really high. Well, let's see. That's 3 plus 7 plus 5 plus 1, which is 10, 15, 16. So that is off the graph already. And again, that's kind of what I expected, right? I expected it to go back up. Let's just plug in -2 and see if this is down off the graph too far. So -2 to the third power is -8. So it's 3 times -8, which is -24, plus -2 squared is 4. 7 times 4 is 28. Minus 10 plus 1. So that is a positive 4 minus 10 plus 1 is -5. Okay, I could plug in -2, or I could plug in -3, but I already know that it's going to be a rather small number way down off the bottom of this. So -3, that's -27, times 3, that's -81. 7 times a positive 9 is going to be 63, minus 15 plus 1, 81, 63, 15, and 1 gives me -32. Okay, so again, there's no real shortcut here to how to get these points. Ooh. And you're just going to make a nice smooth curve through all of them. Now, I don't know exactly, I know that's 1/3, right? I don't know exactly how far down that goes, right? But, it doesn't go super far down. So we would need some sort of graphing calculator or some knowledge of calculus in order to figure out exactly how far down that turning point is. But that's beyond the scope of this course. All we really want to do is to mostly be able to answer all of these questions about the polynomial. Okay. Let's try one more, but we'll skip the graph. So let's try, yeah, let's try this one. Let's see what happens. Okay. Actually, let's take an odd one. So let's take or an even one. All right. So let's do the. Whoops. I think I have another one here. Yeah. Let's do the x to the 4th power. Okay. So degree and number of terms is a quartic polynomial of 1, 2, 3, 4, 5 terms. And behavior is left goes up, right goes, right goes up, because it's positive and even. Maximum number of turning points is 3. Number of complex zeros is 4. because those are the degrees. One less than degree, the actual degree. Real zeros, it could be all of them. And then because imaginary zeros come in twos, have to go down by an even number, and the number of imaginary zeros goes up by twos. Can't go to 6 because I only have 4 answers. But look at all these, they add up to 4. I could have 4 real, 0 imaginary, 2 and 2, or 0 and 4, 0 real, 4 imaginary. It's possible to make a graph that turns 3 times and never crosses the x-axis. Kind of like that. All right, so let's pull my function down one more time. Whoops. Okay. And we'll put it right. Yeah, we'll put it right there. All right, so possible positive zeros. This is now Descartes' rule of signs. So we're looking for the sign changes. So that's 1, 2, 3, 4. So that's 4, 2, or 0. Go down by 2's. And then to analyze the next piece, everything, and sometimes I do a little shorthand. Instead of writing the whole formula out, I just say, well, this one stays positive. That changes to positive because it's odd. That stays positive. That changes to positive. That stays negative because it is no degree. So I can see that there's only one sign change in this. So if you don't want to write the whole function out, f of negative x again, sometimes this little trick is what I use to just figure out because that's all you really need it for, right? We're just analyzing the possible number of negative real zeros. So now, possible rational zeros. It's basically all the factors of 72. So we just got to list out all the factors of 72. So 1, 72, 2, I'm going to do it this way so I don't miss any. 36. Yeah, 3, 72 divided by 3. 24, 4, 5, no, 6, and 12, 7, no, 8, and 9. So we have 24 possible choices here for when we start guessing the factors. Okay, so let's try this out and let's see if we can get our actual factors. Okay, again, I'm going to start at the obvious place, 1. And I need to get this down to x squared in order to be able to factor it. So that's 1, negative 2, 1, negative 18, and negative 72. 4, 3, 2, 1, 0. Okay? Let's hope for the best. Multiply, add. 0. No, that's not going to work, right? Because that's 0, negative 18 doesn't cancel. Just go to negative 1. Okay, bring it down. That's negative 3, a positive 3. So that's 4, negative 4, and not going to be a 72. So 1 is out, and I like to just keep going in order. So let's try 2. And so you can see that this might take a while. Unfortunately, there's not a real better way unless you want to plug this into a graphing calculator and see if you can get the roots that way. 0, 0, 1. No, not going to work. So let's try negative 2, and hopefully we'll have a little bit better luck here. So this turns into negative 2. That's negative 4. That's a positive 8, which is a 9. That's a negative 18, which is a negative 36. And 36 times 2 is a positive 72, so that works out. Okay. Now, that's not enough to factor this, unfortunately. Oh, look, it kind of is actually, because it will actually factor by grouping. All right, but pretend that you couldn't see that. So it's still x to the third power, right? We only reduced the power by 1. So now you have to start guessing rational roots again. Don't start there, right? If you factor something out, look at 72. If I factor a 3 out of 70, right, 7 didn't go into 72. Right? If I factor a 3 out and get 24, 7 doesn't go into 20. No, yeah, 7 doesn't go into 24 either. Okay? So if you divide out a polynomial, if you divide out a linear factor, the linear factor that you tried before is not going to work. But that could work because it could be a multiple root. So what you want to do is you want to always check each root over again until it stops working. If you're going to go at a sort of a logical step through this. So that's -6. That would be -12 and not going to be 36. And in fact, because I can see it, I'm going to jump right to -4. I'm going to skip over 3. So that's 1, -4, -8, which would be a +32. Nope. Let's not -4, +4. Okay. So 1, 4, which gives me a 0, 0. 9 times 4 is 36, which now leaves me with x squared plus 9, which does not factor to real numbers. It factors to x plus 3i and x minus 3i with the sum of two perfect squares. So that means my factors are x plus 2 from this root, x minus 4 from this root, and x plus 3i and x minus 3i. And my answers are -2, 4, plus or minus 3i. Okay? And that is how the fundamental theorem of algebra sort of takes all the stuff that we've done in the previous 5 sections and smushes it all together. That was a little extra from the textbook, but I think it is very useful to see how all this stuff goes together. And number of roots, 4, 14, right from the fundamental theorem of algebra. The biggest exponent tells you how many roots the function will have. That was 5-6, the fundamental theorem of algebra.